So what is the VO2 slow component? We've kind of shown what happens, but what is it? What is the physiological justification for this? Well, to help us with this, we're again going to use the work from Burnley and Jones, and they write this. It remains a source of frustration among those working in the field of VO2 kinetics that this important facet of the VO2 response is, if not unknown to the scientific community, inadvertently or perhaps even deliberately ignored. The blame for its lack of acceptance must lay firmly at the door of textbook writers and teachers of exercise physiology, who with few exceptions continue to insist that VO2 rises to achieve a steady state at all power outputs up to those requiring VO2 max. That is not the case. You've seen it already. You get a steady state condition, what we call a conventional steady state condition in the moderate domain. You achieve a sort of steady state condition in the heavy domain, but absolutely no steady state occurs in the severe domain. And they go on to write this. Our frustration stems from the fact that the existence of the VO2 slow component has been evident for at least 40 years. Astor and Salty in 1961, Whip and Wasserman in 1972. And its presence during any bout of exercise has major implications for the description and assessment of exercise intensity and for computation of the oxygen deficit and rates of substrate utilisation. In other words, it is negligent not to understand and not to be able to record the VO2 slow component, because as you're about to see, it tells us an awful lot about the energetics of our participants. And what is it? Well, this is from Peter Krustrup in 2009, and he writes this. Essentially, the VO2 slow component reflects a loss of muscle efficiency. That is, maintaining the same work rate requires a progressively greater energy turnover with time, which is reflected in a continued fall in muscle PCR and a continued rise in VO2. So what do they mean by a loss of muscle efficiency? Well, we've kind of seen this previously in a previous session when we looked at this graph here. And this really does show us this loss in muscle efficiency. So here we've got the running speeds going from 16 all the way up to 20 kilometers an hour. And in each of these, they've recorded the VO2 response. So here we've got, and you can work out that this is moderate, because if you look after about 4 minutes, which is what conventionally most textbooks will refer to, notice we've overcome the deficit, we've got a steady state. Go to 16.5 kilometers an hour and look what happens. It looks like at about 4 minutes, close to 4 minutes, it looks like we're reaching steady state. But then you get the acceleration in VO2, and actually what you start to find is we don't reach a steady state until around about 6 to 8 minutes. Because you've got the slow component here. And you can see that in all of these exercise intensities from 16.5 to 17, 17.5, there's an ever evolving, can you see they're starting to level out? There's an ever evolving slow component. But once they get to 18, 18.5, 19, 19.5 to 20, we know, because the VO2 has risen to VO2 max, that they must be above maximal lactate steady state, or if you want to call it critical power, if you want to call it respiratory compensation point, they're above that second boundary. So this absolutely does relate to the loss of muscle efficiency. Well, how do we know that? Well, this is a really neat example of this. So here you've got some data where what they've compared is the VO2 response in population with different proportions of fast and slow twitch muscle fibers. And so what you see is if you've got a higher proportion of type 1 muscle fibers for the same exercise intensity, here's the VO2 response, and it starts to level out. In fact, you get almost no slow component. Reduce the slow twitch fiber response, look what happens. You get a slow component here. So what does this tell us? The VO2 slow component is a function of loss of muscle efficiency because you have to recruit fast twitch muscle fibers. Remember that as soon as you start to go beyond gas exchange threshold, you are having a greater rate of appearance of lactate than you are a rate of disappearance of lactate. Why? Because you've got less inactive slow twitch fibers coupled with a greater recruitment of fast twitch fibers to meet the increase in the exercise intensity. So, and it is that recruitment of those fast twitch fibres which is reflected here. They can use oxygen, but their ability to use oxygen is far, far, far inferior to slow twitch fibres. So the net result is the slow twitch fibres are reaching steady state in about 3 to 4 minutes. Those additional fast twitch fibres which are being used to meet the ATP turnover rate are taking about 6 to 8 minutes to reach a steady state. So the slow component reflects fast twitch muscle fibre recruitment. And when we're in the severe domain, remember that VO2 never reaches steady state. It just simply means that VO2 keeps rising. Now this gives us a really important message and reinforces what Mark Burley and Andy Jones were stating, which is this. You cannot use the term percentage of VO2 max to describe exercise intensities. You can't really use the percentage of heart rate max, because remember that heart rate follows a very, very similar pattern to VO2. Why? Well, if I ask somebody to exercise at, say, 90% VO2 max, which is probably in the severe domain, they're never at 90% VO2 max, because fundamentally they're at 90% VO2 max at the start, but VO2 keeps rising inextricably really to max. The same in the heavy domain. I want you to be at 90%, so 60% VO2 max. Well, they might be at 60% VO2 max after 3 minutes, but actually the true indication is what's the percentage of VO2 max at 6 to 8 minutes. So you have to be very, very careful in terms of the way in which you now prescribe exercise. You also have to recognise that exercise that's in the heavy and the severe domain comes at a cost. That is a greater deficit at the onset of exercise, but a proportional increase in the fast twitch fibre recruitment. And it explains, although it's beyond the scope of this session, that explains why the EPOC, that is the excess post-oxygen consumption, is disproportionately high in the heavy and severe domains compared to the deficit, whereas the EPOC in the moderate domain is matched to the deficit at the onset of exercise. And so this is taken again from Dave, Paul and Andy Jones. They come up an awful lot in this lecture because they're very much at the forefront of this field of exercise science. But it really shows for us kind of the relative contributions to the slow component, with really greater than 80% of that contribution coming from a loss of muscle efficiency. And if we then just look at this is a really nice representation, and this is from Jamie Pringle and his group, which are 2003. And what they've done is they've just done a simple correlation between the slow component, so that's the percentage of energy expenditure for the slow component, against the percentage of slow twitch muscle fibres. So the greater the percentage of slow twitch muscle fibres, irrespective of whether you work in them in the heavy domain or the severe domain, and irrespective of whether you're in the heavy or severe domain, the greater the percentage of type 1 muscle fibres, the smaller the slow component. Because fundamentally you are going to reach a steady state and hold that steady state. Whereas if I'm having to recruit more fast twitch fibres, the net result is that it takes longer for those to reach a steady state. And kind of fitting this all together, we can kind of see where the O2 kinetics phenomena sits. In previous sessions, if you've not gone through them, please do. We've covered economy, we've covered lactate thresholds, LT1, LT2. We're going to cover critical power in another session, but it is a proxy indicator for what we've already learnt, which is maximal lactate steady state or respiratory compensation point. And we've learnt about VO2 max. They're all kind of our exercise parameters, but they're linked to performance, and they're all linked through oxygen uptake kinetics, because the rate at which we use carbohydrates, the rate at which we store heat, the rate at which we decline the anaerobic capacity, the rate at which we accumulate metabolites is a function of how quickly one can reach steady state, and the rate at which we reach steady state is a function of these underlying responses here, and these are then all linked to exercise tolerance.